Hello. Good morning. Welcome to day 2 of Earth Mining Forum, second of Earth Mining Forum. And there's a big change. We've seen sun at the end. Yeah, it's a shiny day. Unfortunately, you are here, not outside. So, thanks for coming. And this is the second day of the second of Earth Mining Forum, which is the last day. And as you know, that the third International Future Mining Conference completed yesterday, and it was a great success. And I'm glad that we merged two groups, and I see a lot of collaborative discussions, which was the biggest aim of the merging two events together. So you see today's event schedule, and we have very good speakers and also a panel before lunch. And our first speaker is Mr. Brian Muirhead. He is the project manager of ARRM, from Jet Propulsion Laboratory, Caltech, NASA. And he gave a public speech yesterday. It was around 400 people, and it was a great speech. So he will talk about the same project and a little bit shorter time, hopefully, Brian. I'll chase you if you don't. Let me read about Brian. Brian has worked on numerous spacecraft and technology projects since joining JPL in 1977, including the Galileo mission to Jupiter and the Shuttle Imaging Radar-C. He was responsible for the design, development, test, and launch of the Mars Pathfinder spacecraft that landed successfully on Mars, July 4, 1997. He was project manager of the Deep Impact project from formulation through CDR in 2002. He worked as the Chief Engineer of the Mars Science Laboratory until August 2004, when he became Chief Engineer of JPL. In February 2007, Brian was named Chief Architect and Program Systems Engineer for the Constellation Program, which included responsibility for the architecture of a new human exploration space-like system to the moon and beyond. He returned to JPL as the Chief Engineer at the Executive Council level in December 2009. Brian is also currently the Project Manager for the Asteroid Redirect Robotic Mission. He received his Bachelor of Science in Mechanical Engineering from the University of New Mexico in 1977, and his Master of Science in Aeronautical Engineering from Caltech in 1982. He is the recipient of two of NASA's Outstanding Leadership Medals for his work on Mars Pathfinder and Constellation. He is the author of High Velocity Leadership, which is published in 1999, and Going to Mars, published in 2004. with Garfield and Judy Reeves students. And I invite Brian to give his speech. Thank you. Okay, so we'll have to use the mic here. Oh, yeah, let's go back to it. Okay.
Good morning. You guys hear me okay without the microphone? Yes. Good. Okay, let's do that. It was about almost 3 years ago when I first presented the concept of what we then called the Asteroid Retrieval Mission to senior managers at NASA. It was on December 4th, a day that has lived in infamy in American history. Luckily, it did not repeat itself on that day. I got support from the senior leadership in the Human Spaceflight Directorate to proceed ahead with this idea. And the idea was to rendezvous with an asteroid, something that's maybe as large as 1,000 or 10 meters, 1,000 tons, and capture that asteroid and bring it back, put it in orbit around the moon, and then visit it with astronauts. To this group, that doesn't sound very crazy, but to a lot of people, it does. We've been through quite a gauntlet of a process over the last 3 years, but we've gotten through every one of those groups. And today we are officially a project. We've been through the mission concept review. We're in phase A. We're moving forward into phase B. And the only thing that's really holding us back right now is appropriations from Congress. And we think now that there's a budget bill that we in fact may get appropriations that will allow ARRM to continue. And I'll explain to you why it's worth continuing in this talk. Acronyms, of course. By the way, how many of you were at the talk last night? Okay, don't fall asleep. It'll be largely the same stuff. But I'll do it a lot faster. The acronyms here, the ARRM was originally the idea, the term we used, but we got lost in it. We kept trying to explain these two different missions. There's the crewed mission and there's the robotic mission. I'm the project manager for the robotic mission, and Steve Stitch at Johnson Space Center is the manager for the crewed mission. But the crewed mission is really going to be one of many Orion SLS missions. This is an important chart to talk to. This really provides the context for why ARRM is getting support today. We are an integral part of the human exploration program. We've been locked in low Earth orbit since 1972. We're now attempting to move out with Orion and SLS and human spaceflight into what we call the proving grounds. Proving grounds is cislunar space. It is far enough away from Earth to force us, into systems that can operate away from the Earth's Earth-reliant environment. But it's not so far away that we can't get back reasonably safely. So this is a proving ground for developing technology. And ARRM system, as I'll describe in a little more detail, is a core element of our thinking and proving ground. It will be basically the first building block of a number of systems that could eventually be present and used in cislunar space. And here is where we would be doing stuff with our international partners. Just as we did with Space Station, we would hope to do things with the internationals in the proving ground. And depending on where we want to go, we can go to Mars, we can go back to the surface of the moon. It's really going to be up to ultimately the decision makers and the players. But a core element is the core solar electric propulsion system, the very high power system that we're building for ARRM. For ARRM to work, we need to have been able to identify, to redirect, and explore. Those are the three building blocks of the ARRM mission. Just a little bit about targets. Now, I mentioned the first the asteroid retrieval mission was about capturing a 1,000-ton boulder. Well, we've since looked at a second option, which is the option of actually going to a larger asteroid and picking up a boulder from that surface. That's NASA made a decision back in December that they wanted to go that way. We had these two options, and I'll describe them a little bit more later. So what you're seeing here is a table of the valid candidate options for the Bring Back a Boulder mission, which is our baseline today. But all I wanted to do with this chart really is just make it clear to you what we care about as we look for targets. We care about the type. We're interested in carbonation contact. It's a major driver for why we went with the pick up a boulder option. And we would very much like hydrated minerals, and that's an area you guys care a lot about. We care about the spin rate. We care very much about V-infinity. V-infinity, of course, is the measure of the velocity of the asteroid as it passes by Earth. And the faster it is, the harder it is to get to and get back from. So we're looking for low V-infinities. We also like things that are close to the Earth's orbit, 1 AU. And again, the absolute magnitude just helps us understand the size. But here you see what we know, the best understood asteroid we have in the solar system, I think, today. Eros might be a good competitor. Power. You can see the quality of the angle we have there. That's the best we have of EV5. That's our target. It's got radar. We think there's boulders there, but we don't know for sure. And here you see a radar imaging that's been used to create the shape model for this asteroid. And again, we won't know for sure we've got boulders there until we get there. But we're willing to take that risk. So why an asteroid? Every time I talk about this mission to politicals and others, they say, we love your solar electric propulsion system, but why an asteroid? The problem with the why an asteroid, I'll be very frank with this audience, is because the president wanted to go to it. And everybody on the Republican side hates everything our president wants to do. So they've been fighting this whole idea of the asteroid. But we've been making this case. First of all, if you're going to demonstrate solar electric propulsion on the scale that you want to, moving tens of tons of mass around the solar system efficiently, you need something to do it with. An asteroid provides that raw material. As I said, we want a carbonation chondrite hydrated mineral object, which has great scientific and resource utilization potential. we want to demonstrate the experience of actually working in space between robotic and human systems, something that we have not done before. And finally, we want to conduct a planetary defense demo, which I'll talk about. All of this is made possible by the presence of asteroid material. So here's our two options. Here's the option A, which was the retrieval mission. It's the objective of rendezvousing with and bringing back a large boulder, a large asteroid. And we used a bag to capture this. The reason we have a bag is because we know very, very little about the structure of asteroids of this size, or even of the big ones. And so the bag was thought of as the way to deal with all the uncertainties. If not knowing what its structure was, if it's a rubble pile, if we start to touch it, interact with it, it'll fall apart. So let's just put it in a bag. And that's what we did. For the option B, the attraction of going to a known C-type, for example, the targets we had for the small asteroid retrieval tended to be S-types. Those are the ones we have found, tracked, and understand best. Not very interesting from various points of view. But if you want to demonstrate our fundamental objective, moving large mass around the solar system, it's a great way to do that. It's a good target. For option B, of course, you see landing here, and I'll show you a great video how that works. But the key to all of this is the bus. It's the spacecraft. It is this machine that has about 55 kilowatts of solar electric power at beginning of life and a 40 kilowatt system of electric propulsion. We'll carry 4 thrusters. We'll use 3 at any one time. And I'll show you the mission profile here in a minute. These are very large spacecraft. The reason they're so large is we need to carry about 10 tons of xenon to do these big missions. Now today, with the bring back a boulder, we're probably closer to 5 tons. And part of what we're doing today also is we're trying to get industry involved. NASA's decided they want us to go buy the spacecraft, which is what we wanted to do. So there's a lot of commercial interest in electric propulsion around the world. So we have an opportunity to push the state of the art in terms of power and EP capability, and basically the overall ability to move large large masses. 5 tons is probably about all the xenon we would need, so the spacecraft would be quite a bit smaller. But you can see that the distinction here between our capture mechanism, a large inflatable bag system, and I'll show that in a second, versus a set of robotic arms. Here's a test bed we built at JPL. When you're dealing with soft goods, and I've got a lot of experience with those, you have to build things, test them, try them out, work out the details. They don't lend themselves well to analytical modeling. So we built a 1/5 scale test bed, and we actually demonstrated the ability to deploy, to capture, envelop, and then retract and control an asteroid body, which would be rotating and oscillating in some way. We did that on the basis or on the back of a robotic arm. And we determined a way by which we could stabilize that whole system, sync it up with the spacecraft, and now basically go for a ride. Because we've now captured something that weighs much more than the spacecraft does. So the dynamics of the system will basically cause us to move with it. And once we've captured it, or it's captured us, we then spin it down and we're ready to continue with our mission. Here's the test bed at Goddard Space Flight Center. They're responsible for the option B capture system. 3 large robotic arms, legs basically, about 7 meters with about 4 degrees of freedom, and 2 7-off robotic arms with end effectors. And these end effectors are very special. They are what we call a microspine. I'll show you that in a second. This whole approach is actually coming out of another body of work that NASA's been doing in satellite servicing. And so there's a little bit of commonality between those systems, and we're attempting to use the investment that NASA's already made in satellite servicing robotic arms, software, sensors to apply to this problem. But it's not an ideal fit. But we'll make it work. So here's the basic mission. We launch a heavy lift launch vehicle, Delta IV Heavy, Falcon Heavy if it comes online, SLS. We have the opportunity to use gravity assist off the moon going out. We don't need it. We fly directly to EV5, about 2 years of thrusting. Once we get there, there's a characterization and other phase, and I'll describe that in a second. After we've been there about 215 days, we're ready to return to Earth and thrusting back for about another 2 years to get ourselves back toward the Earth-Moon system. And through the precision navigation that JPL is quite famous for, we will fly a close flyby of the moon to a gravity assist, which boosts us into a crew-accessible orbit. Now, there's a variety of orbit options. We have One of our favorite ones is a very stable orbit, stable for like 30,000 years. So we can leave it there as long as we want. But there may be other orbits we may choose to use. Once we're at the asteroid, this is the process that we go through. We approach. We spent about 72 days characterizing. This is detailed mapping of the surface, centimeter class detailed mapping, looking for our boulders, that are ideally sitting right on the surface, the right size. But we will not know the nature of the boulder, the nature of the surface, until we actually touch it. Now, we may carry scientific instruments, spectrometer, for example, it gives us a much better sense of what material is there. But knowing the density, knowing the structure, all of those things are unknown to us until we actually touch the surface. And that's what we'll do. We fly down and we basically free fall and land on top of a boulder about the size of these guys over here. Nice boulder over here, 3-meter class. But we land. We've got to do precision terrain relative navigation. We've got to land around this boulder. We've got to land on terrain. And we won't know for sure what happens until we touch down. And we may sink a little bit, that'd be fine. Then we've got a grasp for the boulder with 2 robotic arms. And on the end of those arms is a microspine I'll describe for you. But here, again, I just can't emphasize enough, we understand the risks associated with the uncertainties here. We'll have to develop a system that's robust to these uncertainties. But this whole phase that I just talked about, the landing, the grappling, and actually the lifting off of the boulder, is completely autonomous. The ground is not in the loop during that entire phase. So we need a system that's built to do that. I'll tell you what, let me do questions at the end, thanks. Once we've pushed off with the boulder, and we'll have multiple targets. I said I want at least 5 good targets, and a baseline 3 attempts. And we have to be adaptive depending on what we learn. With the first attempt, we have the ability to let go of the asteroid or the boulder at the time, either after we've lifted off or while we're right there. There's a lot of ways that we have to be capable of escaping if something goes wrong. Once we're off, though, assuming we're grabbed our 20-ton boulder, we do this planetary defense demonstration, which I'll describe in a second, and then we're ready to return and head back to Earth. This is the microspine system, and the animation I'll show you in a minute really illustrates how this thing works. But this is was actually built from early concepts that one of our engineers, Aaron Carnes, had developed around the finger of a gecko. How the gecko is able to crawl up and down windows and walls and whatnot. And so he's taken that concept and he's turned it now into a mechanical version, which has thousands of little microspines, which actually are able to grab the boulder surface. Now, the question is, what is the boulder surface? What simulant should we be using? How strong is it? Those are big uncertainties. We've got a group of about 30 scientists helping us try to characterize that as best we can. But we're still going to be faced with a lot of uncertainty associated with that. Now, come on, you guys. I joked last night. The dinosaurs did not have a space program, and therefore they got blasted by an asteroid 65 million years ago. We do have a space program, and part of what we've been doing is at least talking about how we would deal with a potentially hazardous asteroid. So there are none targeted to the Earth that we know of at this time. We are looking and continue to look. But with ARRM, we have the capability to demonstrate what we call a slow push technique, where we use, in our case, a gravity tractor. The gravity force between the large asteroid and our spacecraft with its boulder is just enough that when we turn on our thrusters at a certain duty cycle, we're able to pull the asteroid slightly out of its orbit, change its velocity just a tiny amount, less than a millimeter per second over the course of about 60 days. Another option we have, if for some reason gravity tractor didn't work, or boulder, we ran out of time or whatever, is actually just use the ion beam of the electric propulsion system and actually just throw billions and billions of xenon atoms at it, and at that way we impart kinetically a change in velocity. And that actually turns out to be a pretty efficient way to do it as well. But here again, we're just demonstrating a capability. The crewed phase. This is, again, a very important, a very unique part of this mission. It's the first time a crewed vehicle will actually dock with a robotic vehicle in deep space. Our vehicle will basically be passively waiting for it. We have a standard docking ring, standard docking interfaces. Once there, and again, the animation illustrates it beautifully, you see the crew egressing, going out and hand over hand, moving across our spacecraft. One of the things I constrained this in trying to implement this project in a cost-effective way is that we will be crew safe, not human rated. So our vehicle is designed to be safe for astronauts, but it is not a vehicle that is human rated. And as we started down this process, our friends at JSC got the neutral buoyancy lab up and running, and using the kind of spacesuits we expect to have at this time of ARRM, which are not ideal for EVA, they actually went in and demonstrated the ability to egress from an Orion capsule, go to a simulated asteroid material, and in this case from a large asteroid, and actually bring back material and do it in only 4 hours. We have an opportunity for only 2 4-hour EVAs. That's all the consumables we have for this class mission. The crewed mission, by the way, is about 25 days. So, for all the rocket scientists in the room, maybe you guys know all this, but just to repeat here, chemical propulsion is wonderful if you want high thrust, but the energy that you have in that system is the energy that's in the chemistry of the 2 reactants. Hydrogen and oxygen is the most efficient chemistry we have today. Electric propulsion, on the other hand, is a completely different paradigm. The amount of propulsion you get is not dictated by the amount of propellant you have, it's dictated by the power you have. The same amount of propellant with more power can give you more thrust. The problem with electric propulsion is it's very low thrust. We've got 3 engines at 12.5 kilowatts each, 40 kilowatts going in. The amount of thrust we get out of that system today is 1.5 newtons. But 1.5 newtons for over 5 years can move a lot of mass great distances. I'll show you a little bit about how we've changed. We've actually fundamentally changed the way we've been thinking about doing human exploration because of ARRM. The work that we've done in defining the EP system, the work what I call our navigicians, people that do these low thrust trajectories, we've shown how we can fundamentally change the way we do our thinking for human exploration in deep space. It used to be all chemical propulsion. The number of big rocket launches it took to get crew to Mars was a big number and a very expensive number. We can now do it in a single launch, I shouldn't say single launch, in a single mission with electric propulsion and chemical. So here's one of our engines. This is a Hall effect thruster. It's different than the ion grid thruster that we used on Dawn. It has some really nice features. It's a much simpler system to operate, and it has the potential for basically infinite life. That's what's really fundamentally different here. We believe at this time, we do not know of a wear-out mechanism for this thruster, because we're going to have to put through this thruster much more propellant than we've ever done through any other engine. We can't really test it on the ground. We don't have that much time. But by analysis and other testing, we can prove out the system. And again, just to point out the difference, an EP system, if you wanted to go to 2008 EV5, and assuming you were bringing back 1,000 tons, this was a full asteroid mission. It would take 18 tons of propellant. It would be basically a launch mass of 18 tons, of which about 10 tons are propellant. If you do it chemically with less hydrogen, it would be a factor of 20. And the number of launches that would require is completely prohibitive. So this electric propulsion is completely enabling for the ARRM mission and for a lot of other things beyond that. Just to highlight, again, a great mission, the Dawn mission, which has been flying for about 5 years now, all completely enabled by electric propulsion. This Dawn mission, though, was a 2.5 kilowatt thruster, carried about 500 kilograms of propellant. We're way beyond Dawn, at least 2 factors. So let's just put things in a timeline here. We continue to look for asteroids. We're going to pick our final target a year from launch. I would bet you today that the target we have today is probably the best target we'll ever find, and that one is 2085. Our robotic mission is currently scheduled to launch in late 2020. That really depends on funding, but if we get the funding profile we want, my team is ready to go build this machine and get it to the launch pad by the end of 2020. 5 years later, we'd be ready for the crewed mission. The timeline for the crewed mission is a little bit, in some ways, more uncertain than our timeline. We did have EFT-1 a couple of years ago now. Very, very successful, but an uncrewed vehicle. The next mission will be 2018 or so, probably, well, again, it's an uncrewed mission. The earliest we would get a crew flying on an SLS Orion vehicle is probably 2023. ARRM would be ready for them in 2025. That might be a little early. We'll see. Okay, now I'm going to show you a video. Let's see if it plays. Here we go. So this is going to tie all the stuff I just told you together. not as hard as landing on Mars. I've done that. But this is not a simple mission. You can see there's a lot of very complex moving parts. So I just wanted to share with you a little bit about what you guys are really here about, which is, from my point of view, relative to resource utilization. So if we're ever to get humans living off the surface of the Earth in a sustainable way, we're going to need to have businesses that are sustainable off-world. And we're going to have an environment where people can live off the land. And we're not there yet. We're not even close. But that's a big part of why you're at this conference here today. We're obviously driven today by the cost of getting mass off the surface. It is very, very expensive. If you can get things in space, make them available in space, that's great. That should be a great building block for business in space. There's a lot of asteroids out there. We're going to get better and better at finding them. It's getting to them and getting back from them, which is where electric propulsion plays, I think, so significantly. And of course, again, I don't have to tell this group, but in my view, the usable resources are obviously water, oxygen, maybe metals, but maybe feedstock for anything that you can do with additive manufacturing. And ARRM has the potential to bring, to partner with industry, with other organizations, with internationals. We're already talking with various internationals. I'm providing a certain amount of volume and mass and power to accompany or to accommodate payloads over and above the core of our mission. But ARRM is a capability demonstration mission. It's fundamentally about technology and human spaceflight. It is not a science mission. We have no science mission instruments at all. But like Apollo, like Pathfinder, we will have great science that comes from this mission. It's just that it's not in my budget to pay for it. So I expect that we'll see a lot of growth and interest as this mission proceeds. Just wanted to point out with this, where EP is a huge game, it's really a game changer in how we think about how we do deep space exploration. Not only in the things I've talked about with ARRM, but also in our deep space science, and eventually even traveling to the stars. ARRM is a tiny step on that path, but there's a certain congressman who really wants to see humans eventually go to the stars, and showing him that this is a step in that direction is very, very powerful. And this, I just want to finish with this chart. This chart is a graphic that shows an idea that one of our engineers at JPL came up with, who's one of our, again, nano-magicians, who said, if I take what EP can do, electric propulsion can do, and I add chemical to it, I get the best of both worlds. This is actually a graphic and a mission design that shows us delivering a habitat with crew from Earth to the Mars system, using electric propulsion to get us to Mars as quickly as we can, 7 to 8 months, and using chemical to get us into orbit. And of course, this vehicle's got to come back. And you basically reverse the process. You get out of orbit with chemical, and you use the EP to sync yourself up back with Earth and get into Earth orbit and return to crew. So with that, I'd like to open it up for questions. Yes, sir.
If you knew there was going to be a problem with the crew mission,
yes,
would you reconfigure the robotic mission to bring the boulder back to near Earth orbit?
We could do that. There's always a little concern about that. We know for a fact that material the size of meters enters the atmosphere of the Earth, every year, 10 meters every decade or so. And there's no risk there. So the problem is convincing people that there's no risk. But yes, we could do that. But the real objective is we want to get the humans out of low Earth orbit. We need to get them, and that's part of why we're the magnet. We're drawing them out. Sir.
Yes, electric propulsion, terrestrial electric propulsion to get us off the station, or out of space Earth's gravity well. Linear motors have been kicking around since rail guns and all that stuff. 11.2 kilometers a second is the escape velocity. Any prognosis on that?
Well, you're talking about launching stuff from Earth with railguns?
That's it.
Yeah. Again, you're launching small masses. It's not something that you can really launch you're never going to launch a crew that way. You could launch some cargo that way, I guess. But I haven't seen a good business case that says that's the right way to go. Yes, sir.
Yeah, question on the EVAs. You mentioned two 4-hour EVAs. My first thought was why so few? Apollo did 3 8-hour EVAs plus a stand-up EVA and way home.
Consumables. and the mass carrying capability of Orion. Orion can only deliver 2 crew to this orbit, given the capabilities it has today. It's too. When I was the chief engineer of Constellation, one of my big complaints was the mass performance of Orion. And so we haven't solved that problem. So in order to deliver 2 crew for a 25-day mission, the amount of consumables we can carry, including suits, breathable, and the ability to decompress and recompress the Orion vehicle, really limits us to 2 4-hour EVAs. That's the best we can do. Now, if at some point, as you build up the capabilities in cislunar, if you can start bringing logistics modules, if you take the ARRM spacecraft, add a docking node, and deliver logistics, now you can have crew up there as long as you want. It's a mini space station. Yes?
Any idea on the precise quantities of the boulder that would be brought back to?
How much we'll bring back? At least 100 kilograms. Yeah, and again, it's not a science mission, but we're talking to scientists about how would you like to sample this? How do you maintain, you want to drill, you want to get subsurface, you want some stuff from the surface. So all that stuff stuff we'll develop and prove out here on the ground before we send the crew up. Yes?
I appreciate the video was probably more of an idealized concept.
Yeah. Boulder was sitting out there nice on a flat field. Yeah, it was perfect.
Exactly.
In my dreams, right?
What I'm curious about is I suppose the gecko thing is like a...
Gecko.
It would seem that the entire mission is almost contingent on that being successful,
Mm-hmm.
even though there's so many variables. And that I suppose the boulder having been elevated off the ground for 3 days. Now, what if that fails? What kind of redundancies will be in place for that? Because everything flows from that being, successful mission in general, everything that comes after, but also from the economic standpoint, and even the fuel that would be required. So, are you working on some contingencies that would factor that in should it fail?
Yes. The question was, we do have contingencies if the microspine system fails. Yes, we do, but I'll be quite honest with you, given the uncertainties we have today, in the nature of the boulder and the nature of the surface and whatnot, this is not the most robust way to go about granite boulder. And at some point, probably in phase B, I will have to have a session in which we really go through and decide, are we willing to take the risk associated with the uncertainties, or is there a more robust way to do it? And we'll have to have that conversation. Part of the reason we're using the microspine is we're leveraging the technology of the satellite servicing community. So we've got 7 DOF arms. We need end effectors. This is the best thing we can do to actually grab a boulder. But if the material is judged to be just too fragile, that the spines won't work, we've got to have another solution.
It seems like the calls seem to require that better elevation.
Yeah.
If it's not successful, the whole thing.
Yeah. Well, yes, but my mission success criteria, first and foremost, is to get that spacecraft back. And if for some reason we're not able to bring back the boulder, the mission will not be a failure. It'll be sad, unfortunately. We'll probably bring something back from the surface, more material probably than OSIRIS-REx can bring back from Bennu. But it's, but my objective fundamentally is to get that spacecraft back. So, yes,
I want to ask
3
about
minutes.
the xenon as the propellant.
Yes, the xenon.
This presumably comes from distillation of air.
Yes, well, yeah.
What's the world's reserves then of atmospheric xenon?
We produce about 70 tons a year. So there's a lot of capability to produce xenon. We need about 5 tons.
Yeah, all right. But what I'm thinking of is, looking at the future, how rapidly is that 70 tons, refreshed in the
There's already, when we started talking about ARRM, the arbitrage market started talking about ARRM. And so they're already thinking about us. So the market will adjust, and we'll probably be buying xenon on the market over several years.
Yeah, I'm not thinking so much of buying.
Okay,
But
the
actually,
production.
The production.
Yeah. I think if for some reason if the market grows, it's not hard to add additional capacity to reduce it.
But are you talking about how much xenon is there in the atmosphere?
Oh, there's
like a limited resource.
No, it's not limited. It's an infinite source. There's more than enough xenon here. Helium, on the other hand, is a limited source.
But it's not in the atmosphere.
All right. Okay. Couple more questions. Yes, sir. Where we have another question?
No, no.
Okay, up in the back there.
I just had a question about radiation shielding for the
Yeah.
astronauts.
Yeah.
Is that part of this project?
No, it's not. It's a real serious problem. And again, there's a lot of uncertainty still around that. But one of the things that actually may turn out to be an efficient way to provide shielding is asteroid material. If you need a certain amount of mass to provide radiation isolation. And that could be a very effective way to provide it. So rather than launching tons of water, basically, maybe to provide shielding or tons of aluminum or whatever, you could use asteroid material. And we've talked about that. Yes, sir.
I was just wondering about how you targeted the asteroid and the methodology. Is it just basically the list of known asteroids, or were you looking for new ones? And also,
Yeah.
for the parameters you listed, some which didn't have a key, it's just a table rather than important.
Well, there's a very rigorous program of near-Earth object observation, and we are identifying, we're cataloging. If you go to this, we have ground-based capabilities. Pan-STARRS is the most sophisticated in Hawaii, and we're scanning the sky looking for asteroids. And every time we find one, it gets a name, it gets cataloged. If it's an interesting one, if it's one that maybe is getting a little close to the Earth, we'll put other eyes on it. If it's one that might be an ARRM target, we'll put special eyes. We'll put the IRTF on it if we can. And that gives us a sense of what it is. And that's what we basically have done with EV5. So we keep looking. But again, our constraints are such that it's a fairly narrow band of targets that we can use for our mission. But again, in your business, if I were, Deep Space Industries or Planetary Research, something like that, what I would love to do is find a 1,000-ton, maybe a couple 1,000-ton asteroid, C-type asteroid, free-flying asteroid that I could go grab with our Option A system and muscle it into orbit around the Earth, around the Moon, whatever. Now I can start experimenting with production and things like that. So we'll bring back enough material, the right kind of material that you can actually do the kind of experiments on a scale that might be useful. And eventually, you guys could even maybe go out there and work on the ARRM target itself. Yes, sir. Last question.
How close you can safely follow 40 kilowatts of electrical thrust of the force? Is it hazardous to be behind?
Oh, behind the ion engines? Yeah, actually. The ion engines are spewing out the xenon at such high velocity that if I'll probably get this a little bit wrong, but if you took a chunk of aluminum and put it in that field, it would basically vaporize it over the course of a year. So one of our issues is actually plume. How do we manage the spacecraft to keep it out of the plume of those engines?
And is that persist for a long time? Like, is it dispersed?
Oh yeah. It's exiting at 30 kilometers a second. So it's leaving the spacecraft. But there'll be a small amount of xenon all around us. Like, this is kind of natural that would happen to the propulsion systems.
Thanks very much, Brian.
All right, thank you.
So no